Hello, hello. Welcome everyone to another installment of LeetCode Live daily streams where we continue doing questions, working towards our goals, and hitting those marks. Today we're starting from, let's see how many questions. We're starting from 237 questions, making our way closer to that 300 question mark. I just came back from a long weekend, a very long weekend. I had Friday and Monday off, so it almost felt, even though today's already Tuesday, which is nice, it's crazy that, sometimes you come back from a vacation and even though you're feeling relaxed, you're also sort of in this like post vacation blues mindset. I mean, I was seeing family pretty much every day this weekend, having a lot of fun, and now it's just back to the normal grind. But it's okay. It's good to work hard and play harder. Rashawn, great to see you again. Really glad that you're here. Happy Monday. Although today's Tuesday. I hope you know that today's Tuesday. So just reminding you. Yeah, today is Tuesday, which is nice. It was a nice Labor Day yesterday. Well, I guess maybe you meant happy Monday as in happy first day of the week. But yeah, it was a little bit slow today, feeling very unmotivated, but that's just how life goes sometimes. So, without further ado, let's go ahead and get started today. This one will probably last about an hour. I'm planning on making it so. So let's see. Let's come to this first one here. Binary tree paths, starting with a nice high quality question. So given the root of a binary tree, return all root to leaf paths in any order. A leaf is a node with no children. So let's see. So it wants us to stringify this first of all. So it looks like, I want to start off with a drawing, since I think a drawing is going to be especially useful here. Let's go ahead and delete what we had before. Let's just draw this out. So we have 1, 2, 3, and then the 5 down here. Okay, so 1, 2, 3, and 5. And let's do this. Okay, so I feel like we're going to need to be constructing a new string, and then anytime we get to a leaf node, we can just essentially append or add the newly constructed string to our array of strings. So what I'm thinking about doing is, let's say I'm going to create this empty array down here that's going to signify our output, and I'll sort of start creating a string anytime I go to a new node, as long as that node is not null. So let's say right here in the beginning, we're going to construct a 1. And I want to make this one smaller here. This will be a 1. Then we come to the second one. Oh, that's not what I want to copy. Come to this second one here. So this will be a 1. Now we're going to add the 2. All right. And then we get to the 5. Now we add a 5. So we're always going to be adding the number as long as it's not a null node. And then if it's the root node, we're not going to also append the arrow going on the right. I think that's what I want to do. I always want to append the number and the arrow, but then when we get to a leaf node, I'm just going to go ahead and append the number. For each one of these different paths that we take, I'll sort of be passing in this string, and I'll be creating a new string in every single stack frame. So the way that I'm thinking about doing this is, let's see, let me actually just expand this all the way now, make this full screen. I think I want to say something like current path is this, and then our paths is equal to an empty array. Here, if we get to something like if not root, let's just go ahead and return paths. Then we can say const new path will equal the current path plus, let's see, we can add the current path plus root.val. Okay, and then here we can say if, let's see, if not root dot left and not root dot right, we're going to also, to the new path, actually, I think at the end here, we can already just append this, right? New path. So here we can say paths dot push new path. This is if it's a leaf node. Else, let me actually make this, let me do a let here. And then to new path, let's say new path plus this string right here. And then what I'm thinking about doing is we can do binary tree paths root.left new path and paths. We can do binary tree paths root.right new path and paths, and then we can return paths. This is what I'm thinking about doing. So if let's go ahead and start looking at this and plan how our code will go. So I'll remove this, I'll remove this. We'll start off with this first one. So the first time we call one here, we're starting off with this empty string, current path. If not root, return path. So this doesn't execute. Now we get to the next piece. Let new path equal current path plus root.val. Right, so now the current path will just be this one. Now, if we're at a leaf node, which this signifies, we can just push it to our path. Else, we can say, let's see, new path equals new path plus this. Right, so now we'll append that arrow to here. And then we'll call binary tree path root.left with the new path. So we'll call it with this thing. Actually, let me just keep this one up here. Copy this. We'll call the left with this string. Again, we check this case here. That's not this. It does not evaluate the true. So we go to the next thing. New path, current path plus root.val. So now we append that too. If we're at a leaf node, which we're not, we do paths.push new path. Okay. Or we do new path equals new path, and we also append that arrow on the right. Right. Now we call this with the next one right here. This is a null node, so we'll just return paths, which in this case, so far it's an empty array. Come back here to the top, and now we're going to call it on the right. Now this here is, this is a, let's see, this is already a leaf node, so now we're just going to append number 3. Now in this case, I can append number 3 and I can push paths. I guess I can still call left and right and return paths, and that should work out fine. I don't think I have to do anything else special here. So let me just run this and see what this gives us. 1, 2, 5, and 1, 3. Okay, looks good for that first test case. Let's see the next one. I have a 1 and a 1. So let's go ahead and submit this. 25.42. Sweet. Now, this is a binary tree, so we can't really take advantage of any binary search tree properties, for example. You know, the fact that the left node will be smaller than its parent, the right node will be greater than its parent. There's nothing really that we can do here. So the way that I decided to do this is actually going to be a pre-order traversal. So pre-order because we do some operation on the current node first, and then we visit the children, versus something like an in order where we visit the left, process the current node, then visit the right, or a post order where we visit the left and right children first before processing the node. So my solution here took advantage of a pre-order solution. If we think about, I guess a pre-order traversal, if we think about like the time and space complexity here, so the time will be O of n because we'll have to visit every single node in the tree to make this happen, to complete the algorithm. So n, where n is the amount of nodes in this tree. And for a well-balanced tree, the space complexity, if you think about the internal stack space, like the stack will never grow to be taller than the, I guess, tallest point in the binary tree. So if we have a well-balanced tree, and I think that means that no node differs by a height of more than 1, in this case, this one is well-balanced, and we can almost safely say that the space complexity will be O of h, where h represents the height of this tree. Now, if we had like a heavily skewed tree, so imagine that like this was just 1, 2, 3, 4, right? Or actually, I'll just draw that out, make it a little bit clearer. Just imagine that we had a tree that was like this, Don't worry about the tree values, the node values. Just imagine that we had that. If we had a heavily skewed tree, then the space complexity would trend toward O of n, where n is the amount of nodes, since we will need as much stack space to accommodate all these different stack frames. And in this case, if we really think about it, this really isn't a binary tree anymore. This is more like a linked list, right? This starts to look more like a linked list and less like a binary tree. It's funny when you think about the ways that we draw these data structures. Sometimes the only thing that makes it a binary tree, I mean, apart from having any other nodes in the tree, is just the fact that we're drawing it like diagonally and not horizontally. So, I mean, I can literally just, can I actually, it'll be nice if I can rotate. Oh, there you go, right? I mean, if I just rotate like this, all of a sudden this becomes a linked list. I know the numbers are skewed and they're rotated, but if you think about it, that's really the only difference in this case. So something kind of interesting to think about. So I'm pretty happy with this solution. I like the fact that we drew it out, we thought about it. It's a very common pattern we'll see in a lot of other questions, but this is a solid traversal algorithm, and I'm definitely going to like this one. Definitely will be adding it to my list later on. Cool. Let's get to the next one now. Sorry, I don't know if you guys heard that, but I had something in my teeth. Okay. Redistribute characters to make all strings equal. You're given an array of strings, words, 0 indexed. In one operation, pick two distinct indices, I and j, where words of I is a non-empty string, and move any character from words I to any position in words j. Return true if you can make every string in words equal using any number of operations, and false otherwise. So let me think about this. Move the first A in words 1 to the front of words 2. So move the first A in words 1. Oh, okay, to make that ABC, and now they're all ABC. It is impossible to make all the strings equal using the operation. So we can pick two distinct indices, I and j, where words I is a non-empty string, and move any character from words I to any position in words j. So I don't think this is so much like, I feel like this is one of those questions where sometimes I get so deep in the details of the question. In my head, I'm already starting to think, and I'm almost getting a little bit panicked, thinking like, oh man, I'm gonna have to go through every single word and every single index and figure out how to move things around. But I think there's probably an easier way. I think our job is here to like abstract this a little bit and really think about what it's asking us. Now, they want the word redistribute characters to make all strings equal. Now, can we be words I consist of lowercase English letters ABC, AABC, and BC? I think what we need here, like, it'd be nice if I knew, like, one thing I think about is like, if I had, like, we have 3 A's and we also have 3 slots, so we can put 1 A in each slot. We have 2 B's, we have 3 B's, and we have 3 C's. I think at the end, as long as we have some amount, like some even amount, we can fit, like, if we have, let's say we have 6 B's, we can put 2 in each. If we have 9 B's, we can put 3 in each. But that's the thing, right? We need to also take into account the length, because we can say, like, for 9, well, 9's a little bit, 9 is actually easy because I can say three characters in each. If we have 6, however, let me see, with 6 characters, can I split it in? Yeah, I guess if I can just split it evenly with the amount of indices I have, is that okay? That's kind of what I'm thinking of. So what if we took the frequency of all the characters, we stuck it inside an array, which I'm going to use an array, a fixed size array, since I see that words length is less than 100, words of I dot length is less than 100, and then words of I itself consists of lowercase English letters. I'm going to start with that, because I know anytime I see lowercase English letters, that's a very good indicator that I can probably use some array. So, and actually, yeah, we can do array of 26. That's going to be like our alphabet frequency. And then we can say for const word of words, for const char of word, what we'll do is we'll say const index equals car dot car code at 0 minus 97. And then in our frequency, we say frequency of index plus or equals 1. Now I think all we need to do is like for every character, it should be, I guess 0 is fine. If we have none, that's okay. We just need to make sure that everything is divisible by the length. Or let's see, like 9 modulo 3 is 0, 6 modulo 3 is 0, 0 modulo 0. That's not a number, so we don't want to include zeros. Although we can make a case for that. Now if I have like 6, for example, because 6 divided by 3 is 2, but it can't be 6 modulo 3, right? Can it? That's one thing we can try. That's almost what I'm thinking, because if we have enough characters that are evenly, but like what if we only have, oh no, yeah, if I have 2 modulo 3, that's 2, so that's not going to work. In here, we have 2 A's, but then we have 1 B. I think what we want to do is we want to say return frequency dot every, and I'll say frec. We can say frec is equal to 0, or let's see, we have frec modulo words dot length is equal to 0. And if this does work, I'll explain to you sort of what I'm doing here. So we have true and true, but I mean, this is maybe a contrived case. Let's look at the second one here. True and false, true and false. Should we just go for it? Should we just, let me try and think of like another edge case. When can this still be true? Like what if we have, yeah, I guess if I have 6 characters now, in one operation, pick 2 distinct indices I and J where words I. Well, let's just go for it, because I was thinking like, what if we have 2 indices? In index 0, we have like 6 A's, right? But then we can do 6 modulo 2, that's fine. We could put 3 and 3. Let's run it. 77.27, very nice. Very, very nice. Yeah, this was another very, very good question. I really like this question. I also like that we took advantage of some of the things that we've learned up until this point. This has been a recurring theme over and over again with, all these different questions that we've done. Before, like I used to have to really try and remember to use this sort of thing because I always saw it as an optimization. And I always used to stick frequencies of characters inside of like an object literal until I found out later that it was actually more beneficial to use something like a fixed size array like I am here. So let's think about what we did. I created a fixed size array because I saw that my bounds sort of gave me the opportunity to do that. These are very nice bounds, only 100. We can easily fit that inside of an array. But even apart from that, I knew that this was lowercase English letters. So I'm keeping track of the frequency of each individual letters by throwing them inside of this fixed size array of 26 to represent all the characters in the alphabet. And then I loop through every single character in each one of my different words, taking the normalized code taking the code and subtracting 97, which is lowercase a in ASCII, so I can map A to 0, B to 1, C to 2, so on and so forth, increasing the frequency. And then we saw that 0 modulo 0 is not a number, so for all intents and purposes, if frequency is 0, that's fine. That's assuming that we just assume it's true for that case, but really we just need to make sure that every frequency inside of frequency is either 0 or the modulo words.length is equal to 0. And that's what every allows us to do in JavaScript. It takes an array and it runs a callback on every element inside of the array. And the nice thing is as soon as it like is false, it'll return immediately. So you can actually save time by not having to iterate through the entire array. So time and space complexity, our bottleneck is going to be this, right? So word of words, like this is going to be an M by N operation. I guess we can do W by C, where W are the amount of words and C is the amount of characters per each one of those words. So W by C, O of W by C for time complexity. And for space complexity, you know, we're really taking advantage of this fixed size array here. So this will be constant space complexity. So very, very happy with this solution. I'm glad we went over this. I'm really happy with the questions we've done so far. It's a good day to do LeetCode. All right, let's see this one. Okay, so you're given a positive integer num. You may swap any two digits of num that have the same parity, both odd digits or both even digits. Return the largest possible value of num after any number of swaps. So yeah, I mean, the first thing I think about is, I guess the parity doesn't really matter the way I see it. 8, 7, 6, 5, 3, 4, odd, even. Swap the digit 3 with the digit 1. This results in the number 3, 2, 1. I mean, we can always continually swap numbers. I think that they just want, we may not swap the digit 4 with the digit 1 since they are of different parities. I mean, at the end of the day, we'll probably always get to a point where we can do, because they're of different pairs. I'm almost thinking, like, do they just want, let me see something. If I do 1, 2, 3, 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. Okay, so this is, no, it's not actually, let's see. 9, 8, 7, 6, 5, okay, that's literally just going down. Given a positive integer, you may swap any two digits of num that have the same parity. After any number of swaps, I was almost thinking of just like sorting the number from like greatest number to smallest number, but as we can see, excuse me, wow, that was like, I was like about to yawn and then some weird word came out. As we can see here, but it can be shown. Note that we may not swap the digit 4 with the digit 1. So if I have 1, 2, 3, 4, you might think, oh, let's make 4 in the, let's put 4 in the first place. But what if we just said like it needs to be the same, so we can do like a 1 and a 3. It'd be nice if we can do, yeah, 3, 2, 1, 4. And then from here, so I guess, do we just always start with like, okay, what's the biggest odd and then even? Although this is even, odd, even, and then odd, odd. This is 9, 8, 7, 6, 5, 4, 3, 2, 1. This is literally them just sorted. If I put some other random number like this, 7, 8, 4, 5, 3. What are the counts? I think that's also something important too. I think what we need to do, let's actually copy that number, because that actually kind of yields something. So how many odd numbers do we have? We have 1, 2, 3. And only 2 even numbers. When we have more, so whichever one is more is the one that sort of starts first. So 1, 2, 3, 4. So whichever has higher frequency starts. If same, pick with the higher number. So in 1, 2, 3, 4, there's 2 even, 2 odd. But see the even, okay, so that does not prove this one, right? Like I can't change this one. whichever has higher frequency starts. If same, pick the one with the higher number. But in this case, okay, so we have 2 odds and 2 evens. May swap any 2 digits of num that have the same parity. 3, 4, 5, 3, 4, 8, 5, 7. Okay. Can we use like a 2-pointer method here, perhaps? I'm trying to think how we can. Maybe we can do that. But with 2 pointers, like we're gonna have to. Yeah, if I do 2 pointers, I'm gonna have to like make this an array, and then to be able to go. I mean, that's a lot of like extra work we have to do that perhaps maybe we don't want to get into the business of doing. So what if I start at 3, 4, 5? I guess what we can do actually is I can like have 2 pointers, like these are same parity, so I can swap whichever. I can make the bigger one come in the front, so I can do maybe this, okay, and now I'll get to an even here, I'll get to an odd, that won't work, so then I get to an odd. But see, then now we lost track of this 5, because the 5 could be useful. There may be other sequences of swaps, but it can be shown that 3, 4, 1, 2 is the largest possible number. Return the largest possible value of num after any number of swaps. Like, it can mean that we have an infinite number of swaps. I can always pick 2 numbers and switch them. That's definitely a key point here, because they're not limiting us. Three, 4, 1, 2. Swap the digit 8 with the digit 6. This results in the number 85675. Swap the first digit 5 with the digit 7. I mean, we almost could kind of also do like a selection sort of thing. But again, we're just given a number here. So how would we? There's definitely got to be a more simple way of doing this. Like, we always want to pick, like if you think about selection sort, right? What are we doing? Like, we're starting, okay, we have I is odd. So we want to find the next odd number that is more than 7, which there's not. And we come to 4. The next even number that's greater than 4. So that's 8. Okay, and we swap it there. We get to 5. See, the next even number that's greater, there are none. The next odd, okay, 5, 3. Let's say we have 3, 4. Oh, that was that one, right? Let's say we have another one like 6, 5, 8, 7, 5. 6, 5, 8, 7, 5. So we say, okay, this first one is even, so find the next even that's greater. That's going to be an 8, so we swap these. All right, now we're at the odd. Pick the next odd that's greater. There's 7. Swap those. And then we're just left with this. That's essentially what it is, right? So that's gonna, I mean, but that's after I make this into an array, right? That's gonna take extra work. Is that the way of doing it? Can't say it's my favorite thing. Because how would, I mean, is that even, what if I did like let x equals number 1, 2, 3, 4? Can I do x? Yeah, x is not iterable. Like, how? I don't even know if we can do like array dot from x. That's just a number. Yeah, that's the only thing that's a little bit crappy. So maybe there's probably an easier way of doing it that doesn't rely on picking things. So let's think about what we just did, right? We're looking at this first one. What I can also do, actually, instead of doing that, maybe we can use the other trick where we pick digits off. But if I'm at a 4, do I have to like continue picking things off until I finally get to that last one? Well, I guess I can just put them in an array myself and then do selection sort. But does that sound good? That doesn't sound good. Can we see related topics? Is there, okay, sorting in a heap. I keep forgetting about heaps, because that will already sort it for us. However, it's not gonna get, let's see, we go to, yeah, I think sorting might be the best one. 87655 65875 87655 3412. Yeah, maybe we can do something like that. Let's try that out. It's not really my favorite thing, but let's say to num array equals a function, or rather, let's just do let num array while num is not equal to 0. We can say num array dot push num modulo 10 num equals math dot floor of num modulo 10. But then that also changes things, doesn't it? Because now it's no longer, oh no, I guess not, because we'll still have, yeah, so now we just want to find, let's see, now we have console.log num array. Let's just run this and see what we get. 4, 3, 2, 1, 5, 7. Okay, that's cool. So for let I equals 0, I less than num array dot length I plus plus. I haven't done a selection sort in a long time. J equals I plus 1. J less than num array dot length J plus plus. So we want to see if there is a number. So let's see, let swapped equals false, and then let's also set our index. Let index equals I. So you can say if nums of j, what's the best way of figuring it out if like the parity is the same? That'd be nice to know if both are even. Do I have to, let's see if they're, yeah, that would be, that's like another annoying thing about this problem. It's easy for us to see two numbers that are even or two numbers that are odd. Now I need to find a number that has the same parity as the other one. Is there like a nice function to do that for us? I'm gonna learn something new today. Check if two numbers have same parity. So is there like a nice straightforward way? This is as fast as faster. Okay, that's same parity. Find the number of you getting same parity for a list of numbers. Say both are odd numbers or both are even. Should we just go for this? Should we just make a function that looks like this? I'm gonna go for it. Let's do this. Oh wait, wrong question. Let's say, oh, let's just stick it in there right here. I think I copied the whole if. So here we'll have nums of I, nums of j. If nums of I, nums j, and 1. Okay, so they're the same parity. Let's see, and that's gonna be that last one. And nums of j is greater than nums of I, we'll say swapped equals true, and index equals j. And then at the end, we can say if swapped, we'll go ahead and do this swap. So now we can say num array of I with num array of index equals num array of index, num array of I. Okay, if swapped, and then we'll say swapped. Okay, and then swapped will just reset to false. Okay, and I think else, can we just break here? Because wouldn't that mean that we never found something that was bigger? Can't we break early from here? I forget. I guess we will find out. So we do that whole thing, and then we return num array dot join, I guess. Although it's gonna be joining it as strings. Well, let's see what we get just from this. Let's see if this crazy function even works here. Okay. So what happened here? If not nums I, and that was the way to do it. Maybe, okay, let's do one that's clearer. Let's do one that's clearer. Let's do this one. If a minus 1 equals, okay, so let's do num, oh, you know what? It's supposed to be num array of I, num array of j. This is something I always do. I always do nums because I'm so used to working with nums. That's a very common name for one of the arguments in LeetCode. 4, 3, 2, 1, 7, 5, 8, 6. I mean, these are 7, 5, 8, 4, 3. Okay, wait. Let's do this. If num array, if they're the same parity, and num array of j is greater than num array I, we set index equals j, swapped equals true. Okay, so now we end this whole for loop, and then we come to the end. If swapped, we're going to swap I with the thing that we found at index. So imagine that we're given this one over here. Our array at the end will actually be the reverse of this, right? 5, 7, 8, 5, 6. If we're here at I, and then we're here at j, find the ones that have the same parity. Okay, these have the same parity, and this is greater than num array I. Okay. Oh, but then we also don't want it to be, yeah, it needs to be greater, but it needs to be the greatest thing, rather. So we should actually say maybe the previous max needs to be, yeah, it's not that it needs to be anything greater than I. We find one that's greater than I, we can save that to a max, and then, yeah, so I guess maybe, do we need to introduce like a new variable here called num array I? If num array j is greater than max, then here we can say max equals nums, or num array of j, index equals j, swapped equals true. Will this work? Still the same thing. All right, let's see why. So index equals I, swapped equals false, max equals 5. I mean, it very well could be this weird thing that we just copied off Stack Overflow, but you know, that's always how it goes. So j equals I plus 1, j less than num array dot length. So same parity. Num array j, which is 7, is greater than 5. So now let's say that max is 7, index is equal to 1, and swapped is true. And then we continue here. Not the same. This is not greater than 7, so we do 6. but these are not the same. So now we're going to swap, if swapped, num_array of 0 is going to be swapped with num_array at index, which is 1. So this becomes 7 and 5. Okay, now we get back to the next thing. Now index is I, swapped equals false, max is now equal to 5. So we find the one that has the same parity, which is 5. Okay, and that's all right. However, this is already starting to be expected, 87655. Okay, so this is already wrong, because yeah, we want to actually find the one that has, yeah, 8 should be first, not even 7. And I guess it does matter because I'm changing the order. I mean, what we could do, and I really also don't like this, but at this point, if I just call reverse here, is that going to give us, do I need to set that back to num_array? 784533412. Yeah, it was because when we're doing this operation here, we're pulling digits off from the right side and not processing them from left to right. Don't love this answer, but I'm just gonna submit it. Let's see if it's even right. Okay, 568, 586. Okay, so I don't really want to spend too much more time on this question. It doesn't seem, it's not as high quality of a question as we have already done, like the first two. So I'm okay with just pausing on this question. We can get to it in a weekly roundup. We gave it a shot. You know, it's whatever of a question. I'm sure I'm probably missing something here. Probably should look into how to use that queue to my advantage. But I'm going to reverse this, so next time we look at it, my thought process is unbiased. Okay. Flood fill. Wow. Okay, so this is a very, very good question. And there's like different ways of doing this question. I think so. Maybe I'm thinking of another one. But this one took me a long time to figure out. And really what this question benefits from is I think here, let's see. Yeah, we're going to do a depth first search here. We essentially go all the way in one direction, you know, filling everything in as according to the algorithm, and then going to the rest of our grid. So let me see if I can draw this out, and let's think about this question. So I'm gonna have this grid. So we have this. I'm gonna have another line over here. Have another line over here. Okay. We're gonna have 1, 1, 1, 1, 1. And this used to work for me with these numbers, and now it's okay. Well, that should be a 0. Okay, nope, I don't want that. 0, 1, 1, and then 0. So return the modified image after performing the flood fill. It says to perform a flood fill, consider the starting pixel plus any pixels connected 4 directionally to the starting pixel, the same color as the starting pixel, plus any pixels connected 4 directionally to those pixels, also with the same color, and so on. Replace the color of all the aforementioned pixels with the new color. So we just want to, we need to go visit every single cell that has the same value as the pixel that we start on, and then add or replace it with the new color. So we're starting at SRSC, which is row 1, column 1. And now it's our job to go through the entire grid and fill in every one with a 2. And then we end up with this. Or not every one with a 2, every one that we can reach from this one. And why can't we get to this one? Because if I go right, this is 0. If I go down, this is 0. So there's no path to the 1. And then here we have 0, 0, 0, 0, 0, 0. We start at 0, 0. We fill everything with 0. And we're actually just going to, we don't do anything really. So if we think about depth first search, let's do something here. Or maybe I can just draw out what I'm thinking of doing. Let me see. Oh, that's the wrong one. A little thicker here. Just give it a color. no, I don't want to make, okay, cool. So let's say we're starting at this first one and we're going to say, okay, this one we can change to 2 because we've already been there. So then we go up, we change this one to 2, and now maybe here we might want to try and going up again, but we can't because we're out of bounds. So we come over here and now we go right. Okay, this is a 1, so we fill this up. From here we start that whole algorithm again. Can we go up? No, we can't. Can we go right? No, we can't. Can we go down? Yeah, we can, but when we go down it's 0, so we just come back up here. Can we go left? Well, we've already been to this location before, so perhaps it's not like worth our time. Like we don't need to go there anymore. So we're effectively done with this location. We come back to this cell right here. We tried to go up, we tried to go right. Now we go down. That doesn't matter anymore because we've already been there, so we can try going left, right? So we can't go up, we can't go right, we can't go down. Here we do the same thing. We've already been up, we've already been right, but we can go down, we go down. We've already been up, we can go right, but that's a 0. We can't go down, we can't go left. And then at that point, we can just like unwind our stack of recursion up until the beginning, and we're effectively left with a grid that has everything already done, everything already filled in, like the flood fill done. So really an important thing to consider is keeping track of where you've been, right? Because if you can get into a loop where you might be still visiting, you don't have an edge case that takes care of like, oh, I've already been here before, so don't recalculate it. So I think what we should do, let's see. I guess we can always check to see if it's, oh, I was gonna say we can check to see if it's already the number, but if it's already the number, if we already make it the number, or rather if like, let's say 0, right? If we say, if there's like a 1 over here and I say, oh, if we're at 0, then forget it. That means as soon as I start this, then I'm going to say, oh, this is 0. And I'm not even going to check the rest of my grid, right? So maybe, let's see, start going up. I can do the right. I can go up, right? Okay, so it's easy for me to check borders, like that's all fine. But now to make sure that I don't revisit a spot that I've already been to, I should only ever mark it as complete once we've already been there. I mean, I could use like another data structure for it, but I don't really want to. I don't want to use another data structure for it. What if we say, no, that wouldn't work either. I was gonna say like if we're at the origin point, but that's also not gonna work. Let's see how we would actually start to code this out, right? We're already sort of decided what it is that we want to do. So I think all we really need to do here is we can say we have SR, we have also SC. We can also do something like, I'll do NR and NC to represent new column and new row. New row and new column. And let's think about this. Well, we can never go, like before we even check the grid we're on, before we do anything, and that anything is going to be changing this value. So we can only ever change a value if we're in a valid point, and it's like, okay, cell needs to be a valid point. Cell needs to be a valid point. Cell needs to have original color. That's something important that we should keep in mind. Cell needs to have the original color, and cell must have not already been visited. So if I try to do this, I wonder, because I'm gonna need to capture the original color, because if I start modifying image, I'm gonna lose track of the original color. So maybe I should say something like const original color equals image at srsc. And maybe instead of here I can say perform flood fill. This will take row and column. And let me actually remove this, because then what I can do here, I can say perform flood fill, passing in SR and SC, and then we're going to return image. So let me take these and put them up here so we can sort of use these as reference points. So cell needs to be a valid point. Means that it has to exist within the boundaries, right? So if, I'm going to split this up into multiple lines here. If row is greater than or equal to 0 and, let's see, image of row is less than image.length and column is greater than or equal to 0 and image of column is less than image of row.length. And if all this is true, we also need to make sure that the image at row column is equal to the original color. Then what can we do? We can say we just want to modify, we want to modify this cell, right? So image of row column is equal to color, and then we can return perform flood fill for all the different directions. Like if I want to go up, I do row -1 in column and perform flood fill row column +1 and perform flood fill row +1 column and perform flood fill row column -1. I want to, well, you know what? Oh wait, I'm opening all sorts of tabs now. I don't even know how I got that one on the left. Okay. Let me close this out. And I just want to run this, see if that even works. 111. Okay, so I literally didn't do anything here. Okay, so perform flood fill with SRSC. So why did that not work? Original color, image. We're modifying image in here. We should have access to image from the scope of this function. Perform flood fill SR and SC and return image. Okay, let's go through this together and see what's happening. Can we undo all these dots? Okay, nice. And that one too. Okay, so we are going to start at SRSC of 1. So when I call this, I'm going to call it with 1, 1. If 1 is greater than or equal to 0, which it is, if image of row, right, is less than image.length, which it is, column is greater than or equal to 0, which it is, image row or image column is less than image row.length, yes, and image of row color equals original color, which is image at SRSC, yes. So already, I mean, I feel like at least this one should have run, but it hasn't because we got the same image back. So something I did in here did not actually work. Well, there's only one thing we can do, right? Let's make sure that things are actually running like they should. 1 and 1, that's fine. Console log entered. Okay, so I never entered. Interesting. So row, yeah, that's true, right? 1 is greater than or equal to 0. Image of 1 think I, oh, wait a second. This should be row. Row is less than image.length, column greater than 0, and column is less than image row.length. That's what I wanted. Let's try this out. Console.log entered. Is it going to be very, very curious? I'm going to assume it was maximum call stack exceeded. That's normally the case with these recursive questions. Oh, 0, 1, 0, 1. We got a little bit closer, but not exactly what we wanted. And I realized that the issue here wasn't because of anything with call stack. It's because entered is not a variable. I think I meant to make this a string. So we have row -1, which is up, row column +1, which is right, row +1 down, row column -1. We have row and column. We did 1, 2, 1, 1, 2, 0, 1, 0, 1. How many times did this run? Okay. Wait. 1, 1. And we go to row -1. Okay, that's 0, 1. Okay. We tried to go up. That didn't work. Now we come back down. We should go right. Maybe a better thing, like it only happened once. Why did it only enter twice? Why didn't it continue going all the way through? Console log entered, image row column equals color. That's bizarre. Console.log row column. Run this again and just let me see. As soon as it went to -1, 1, that should have, like, oh, is it because, you know what? This is, what's most likely happening is this might be short-circuiting because it sees that maybe this is false and it doesn't even attempt to do the other ones. Maybe instead of return, maybe I don't really need to, like, what if I just had this instead? I don't really need to return anything since I'm just modifying image. Like, will this yield better results? If this is actually an issue with short-circuiting, that would be like a very great example. Oh, that's so cool. So I think that was like a nice example of like what short-circuiting did. Like it got to that first and it evaluated to false, or I guess in this case it didn't return anything probably. It just implicitly returned undefined, which is a falsy value. So it just decided, well, the rest of the statement is going to be false anyway. So I'm not even gonna try to finish the rest of this, and it returned early. I'm assuming that's what happened. And if we remove this console log here, we should see the result at least for that first one. So they do match. And for this second one, row column, okay. So is it a maximum call stack exceeded? Okay. So I think what's happening here is now all of them are zeros, right? So even though, let's see, if image color is equal to the original color, we can keep filling them up, but that will always be the case because we're just changing zeros to zeros. So now this is when the piece comes of like, we need to make sure we haven't visited this area before. And I'm so hesitant to like use, what if we make sure that like, because I'm guessing at one point it will make it back to, because I was gonna say no, it shouldn't be SRSC color if we're currently sitting at the origin. No, because I want to be able to do anything. I really don't want to create, I don't want to create another data structure that keeps track of this though. Let me think about this. Maybe that's just what we need to do. Create another data structure that keeps track of coordinates that we've been to, like visited. But now visited, what? Do I just want to make the key to visited be like SR plus SC? If it'd be nice if we can do, I mean, we could have visited equals new set. So we'll visit it, and I can say visited, not visited dot has. Let's see, I can create some like weird looking key, like SR, SC, and this should actually be row column. Not visited dot has, and then here we'll say visited dot add row column. Like, will this work? Wait. We need to also pass visited here. Getting a little bit ahead of myself. You said maybe in your if condition we can return the image. And what do you mean by that one? Not visited has, oh, and. Oh, it worked for the second one. Well, let's submit this and see what we get. 89.40. Sweet. Are you saying, Rashawn, that you felt like we don't have to keep track of the places that we visited? Is there a way that we can use the existing image for this to mark places that we have visited without using a set? Because that's just like, that's more data we have to carry around with us, right? I'm thinking here. Sometimes we can like modify the values of previous cells. What we can also do, I just realized this. Would it be faster if we went to check in Discord? I have not, well, I log into Discord all the time, but I've just been more like busy with work recently. I'm so curious. Flood fill, return image, if return image. So we have if, okay, first color is, all right. Oh, 1 second, my dog is not very happy. Image source not equal to first color or image src. Okay, so we have the first color, return image, color and first color. Oh, see, that's almost what I was like trying to, if sr, well, do we even, oh, I see what you're saying. Like anytime we get, so maybe instead, because you're just saying if the origin point, if this is already equal to, if it's not equal to first color, or trying to like wrap my head around what this means here. If it's not equal to first color, or it's already equal to color, we just return the image. me see. Let me remove this. Let me remove visited. Let me remove all these visiteds. Yep, you said to do this and I tried it. Nice. Yeah. No, so if image and image row color equals original color, return image. So like I have this part, but then or equal to color and not equal to first color. I don't know why I'm so confused about this here. No, yeah, I see the params. Like there's color and then there's first color, which is this image SR and SC. I'm just trying to figure out why that works. I guess because at any point, if we're already, but like, image row is original color. Maybe this needs to be, like I only enter this if it's not equal to original color. Is this gonna yield the same? Did I lose a parentheses here? Oh. One 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 110 101, and image row color is not equal to original color. No, I understand that. Like I get the params. I just still don't know why it works. Return image, or we just do the rest and then return image at the end. It's almost like the opposite. Here we're saying that if it's ever out of bounds, or the thing that we're on already equals the color that we want to do, so that needs to be the opposite here for me. So here we're saying don't do this if it's equal to color. So I probably should have where color is what for you, color is that. So if it's not equal to color and image of row column is equal to original color, yeah, perhaps I just need to do the inverse of whatever you did, because I think you're doing the opposite. Yeah, I think that's what it is. Let's see. Nice. And this works because, so yeah, the color and the original color are the things that are kind of confusing. If it's not already equal to the color, if it's not equal to color, then we should go in there. And it's equal to the original color. Right, because it needs to be, it can't be equal to the thing that we want to set it to, but it also needs to be equal to the original one so we can change it to color. I think that's like kind of the way of thinking about it. Yeah, this is one of those like clever ways of not using like an auxiliary data structure to keep track of this. And I also like that you were able to do it with just the original. Like I had to create this whole new function here. So now let me do the thing that I was going to start the first time. I think I was already kind of trending to there. So yeah, original color is image of SR SC. I think really here I can still keep that. Let's see if if row, okay, perform flood fill, return image. Although I guess maybe we'll actually need more. It's for every single time. Well, let's see. Let's just see what this does. And maybe I don't even need original color defined twice here. Yeah. Does this work on its own? What did I mess up here? Oh, row is not defined. SR, SR, SC, SC, SR, 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 SC, 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 SR, 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 SR. Perform flood fill, and now is this going to be, oh, this is also not, yeah, no, and that's definitely better. So it's very cool that you're, it's cool that you're like trying the things out that I'm talking about out here. K equals image. Oh, okay, we also don't have color, an original color. Let's try this. And also we're gonna need to pass an image in all these. Yeah, this I think is the best way of solving it, because we don't use any auxiliary space. We don't need a set like Rashawn pointed out. And at least in my case, I don't need to be creating another inner function to handle it. This just looks cleaner, like keeping it fully contained within the body here. So, I mean, this is a depth first search. So is it just O of V plus E? Like if we think about this as a graph, this is just all the nodes and all the edges in between them. Is that how like DFS? Honestly, I'm always like forgetting O of V. In the case of a graph, the time complexity is O of V plus E. So is this also V plus E? Let me just go through here. O of N. And do they do it the same way? Yeah, DFS. Where N is the number of pixels in the image, we might process every pixel. Size of the implicit call stack when calling. Okay, that space complexity makes sense. I guess N, we have to process every pixel, but if I consider it like a graph, say color starting as flood fill the entire, we use a function DFS to perform a flood fill on the target pixel. We get a stack overflow over. Thank you very much. It does similar things as 200. Yeah, this is definitely a hard question though. This is one of the harder easy questions, but still very happy that we were able to go through it. Highly recommended question. I've done this question multiple times, and every single time I fail on this part. So let's hope that this is the last time I forget about this trick right here, or really these two lines, and don't make the same mistake if I have to come back to it at a different point, because I have done this question and I always feel like, oh, I'm going to use a set because I forget how to think of this case here. So anyway, we're just over the hour. It's been an hour and 15, a longer stream today. Let's see how many questions we did. I think we only did 3, maybe 4. 240. Yeah, we spent quite a lot of time on that last one, but that's fine. That's the point of these. We're going to continue moving forward in our journey every single day. If you like what you see, make sure to subscribe to me on YouTube. Always putting out content there, making these videos every single day for all you to enjoy. And ring that notification bell if you want to make sure that you get the videos as soon as they go up. Thank you to everyone that watched. Hope to see you all again tomorrow, and I hope that you all have a great rest of your Tuesday. See you all next time, and happy